intestinal phase. All we've talked about so far was our pancreas. We've talked about our liver as well as the gallbladder. So we're done with our accessory organs. We're going to continue on through the journey through the alimentary canal by finishing up the small intestine and then talking about what happens in the large intestine. And the small intestine, we namely divide the different areas of the small intestine by looking at the duodenum, the jejunum, as well as the ileum. So you heard these terms when we talked about our, specifically our gastric bypass. We saw where the jejunum comes in. But the duodenum is going to be the important part because that's where we saw the hepatopancreatic ampulla, where we saw the dumping of bile and our pancreatic juices. And it's called the duodenum. The early definition of the duodenum was 12 finger widths, hence the term duodenum. The first 10 inches are going to be the area that we'll talk about where we see continued digestion, and then we're also going to be able to see absorption. So these are the main other functions that we do need to look at. Again, reiterating the small intestine, we continue with digestion, and we start the process, we continue with the process of absorption. We saw a little bit of absorption that takes place in the mouth, a little bit of the absorption that takes place within the stomach, and then the bulk of where all the absorption takes place is the small intestine. So we've got to absorb our nutrients, we've got to absorb our vitamins, we've got to absorb our glucose as well as our amino acids, and then we'll look at the absorption of our fats, and then namely of all the things of all the secretions that we saw, we need to also absorb the biggest bulk of water. We have about a sum of 7 liters worth of water that we need to absorb, and that's all going to take place within the small intestine. This point right here that mentions the length of the small intestine is actually kind of scrunched up, and that's due to the smooth muscle that we'll be able to see later that holds the small intestine together. The small intestine works together. We'll see how mechanical digestion continues. Chemical digestion, we already know, are going to involve the enzymes. The mechanical digestion, again, is going to be the muscle movement that takes place within the muscularis layer. And that movement that we can see is what's called segmentations. So segmentations are the churning that takes place within each segment of the small intestine. And I'm not talking about these different segments. I'm talking about within little pieces of the small intestine. So if I could take a look at this little chunk, there are segmentations that are taking place to help mix. What I want to help illustrate is that the segmentations are not for the purposes of moving food through and moving it quickly. It's what we do to mix the stuff together. We got a bunch of chyme that's been dumped out of the stomach into the duodenum. You've got your pancreatic juices, and segmentations helps mix that stuff together. Because we've got our bile, we want to make sure that bile penetrates through the chyme. You want to get good mixing to help optimize the amount of absorption that's going to take place within the small intestine. So where this segmentation starts, it starts off right by the pylorus, and it pushes through and makes its way into each little stretch of the small intestine. So this is a reflex that takes place once that small intestine starts filling up with chyme. So what we're trying to do, again, the main idea in the small intestine is not to speed the rate at which we're pushing our chyme through. That doesn't make sense. We want to actually slow that process down. So what we saw in all of our blood vessels, right? All of our blood vessels, the arteries, the veins, we saw smooth layers of the endothelium. And we wanted that to create optimal flow so we can have uninterrupted blood flow through that vessel. We're going to see the exact opposite of that in the small intestine. Why? Because we want to slow that process down. So what you see in the mucosal layer are these circular folds, and they're called plicae circularis. These ridges are all present within the small intestine. And here you can see the jejunum actually cut up, and you can see all these little folds that chyme is going to make its way through. So you've got this, the small intestine, you've got segmentations that are coming in, and that's helping mix all of those pancreatic juices with the bile, with the chyme, and that's going to help optimize. You've got all this chyme that needs to travel through this rigid structure, or not, I'm sorry, the rigid, that's not even a word. All these little folds that needs to make its way through to encourage turbulence. And we want this turbulence to slow that process down. So with that, we have this increased surface area due to that plicae circularis. So we want increased surface area to slow this down. What it's doing is agitating that fluid as it makes its way through, that chyme that makes its way through the small intestine. Now, on top of the plicae circularis, we're going to start to zoom in on each of these folds. And we can take, again, a histological slide. Watch it now, this is just more of a cross-section. But we can cut that plicae circularis and look at it on a tissue. Here you can see it on an organ layer. Now let's zoom in and take a look at a tissue layer where, once again, you can see the longitudinal layer. That's all responsible for the longitudinal layer of the muscularis. For the purposes of creating segmentations, we got our muscularis layer, we got our submucosal layer that'll provide the arterioles and the venules. The other thing you'll see are the lymphatic vessels that are also present, and also all the connective tissue that will hold the epithelial cells on top. And the epithelial cells on top, the structure of these are not just going to be one simple layer cell thick. In fact, what you would expect to see are what are called villi. And these villi are just the inherent structure of all these epithelial cells. They're all coming up and they create this, a bunch of little appendages that stick out on top of the plicae circularis. So here you see those folds on top. You see all these little, what they call technically they call this the brush border. And that brush border helps, once again, increase the amount of surface area. So now you've got fluid trying to make its way through. And within these villi, you'll see the structures. So within the epithelial layers, you'll see the capillary bed, and you'll see these lacteals. Lacteals are extensions of the lymphatic vessels themselves, which I'll talk about on the next couple slides over. Okay? So increased surface area on the mucosal tissue. Now, if I can zoom in onto the cellular layer, now I'm zooming into one of these epithelial cells, and on top of the villi, you'll see microvilli. And microvilli are appendages on the apical side. These are going to be very similar to cilia that are right up on top, but they're not really for the purposes of moving fluid. All they do is just to increase the surface area on a cellular level. So what that does for each columnar cell present on these villi increases that surface area quite a bit. So now that gives us more absorption that can take place. So all of these combined, the microvilli, the villi present on the mucosal layer, and the plicae circularis, all increase surface area. Why do we want that increased surface area? That gives us a good interface at which the capillaries we've got a lot of capillaries right next to exposed epithelial cells that assist in the absorption. It's a good interface where we can allow the absorption of all the things that we need to absorb. Now, looking at the crevices, you can see deep within the villi, you still do get the intestinal juices. Intestinal juices are also secreted. We don't talk too much about them, but these intestinal juices basically assist. They're the same things that the gastric juices, same thing that pancreatic juices come in. These come in to assist in additional digestion. Here you saw trypsin. Trypsin comes in and allows for the breakdown of our proteins. They all get activated by stuff that's present in the intestinal juice, and that helps activate our breakdown, the catabolic breakdown of these proteins. There's other enzymes involved which you don't need to know, but there's other what are called colipase that help break down additional fats. Again, moving from big molecules down to small molecules once we make our way down the intestine. This just describes the microvilli. Here you can see the simple columnar cell. This is the actual electron microscope that shows what the intestinal brush border looks like. It's called a brush border because it looks like a brush. You've got your columnar cells here, and you've got all these little appendages, microvilli. These actually happen to be on top of the villi themselves. So numerous iterations of these appendages that help increase the surface area. Now, what are we going to absorb, or how do we absorb? So the things that we've already broken down. We've taken our carbohydrates and break them down into glucose molecules, glucose and other monosaccharides. We have our proteins that are present in our food that get broken down to amino acids or smaller peptides. And then we had fats that were broken down into fatty acid molecules, but a good chunk of the fats were also emulsified by bile. Okay? So looking at each of these portions, you'll see that almost all of the absorption that takes place within the intestines, 90% of that takes place within the small intestine. You'll see our proteins, nucleic acids, and our sugars are absorbed into the capillaries. Either they're moving down simple diffusion, down from a high gradient, a high concentration down to a low concentration. You've got active transport to transport them against their concentration gradient, if that's the case. Our fats have a different mechanism for absorption. Remember, these are emulsified. We have to absorb these through a different passageway. How do we absorb these fats? These fats become covered in proteins. So not only are they separated by bile, but they'll get coated with proteins, and they end up being called what are chylomicrons. So chylomicrons, as I mentioned, things like your peptides and your capillaries get directly absorbed into the capillaries. Chylomicrons, on the other hand, will enter the lymphatic system. So these vessels, again, are called lacteals that project right into the villi. And these chylomicrons allow those fats to get absorbed right into the lymphatic vessels. So those lymphatic vessels will make their way in. They'll return those chylomicrons, and they'll dump that right back into the left subclavian vein. That'll make its way into the superior vena cava, back into the right atrium. So completely different pathway than that of absorption through the capillaries. Why is that the case? Actually, I don't really know why that's the case, but if you were to take a look at the content of blood, you could typically see with like with a particularly fatty diet, you'll see the presence of the fats that are absorbed through chylomicrons separately, as opposed to that the same mechanism we absorb our nutrients through the capillaries. The next thing we'll move on to, any questions on the small intestine so far? We'll cover the last bit, the large intestine, and I'm definitely not going for a whole hour now that I think about it. I'm almost done. Large intestine is going to be the last piece. So again, small intestine is absorbing a good amount of the nutrients, absorbing a good amount of all the different monomers that we've looked at. The large intestine is going to continue on with water absorption. So looking at the length of the large intestine, about 5 feet, of which you can see the ascending, the transverse, and the descending colon, and then the sigmoid colon. So 4 main parts of what we're going to be looking at, of the colon itself. There's other areas that might not be overly important, or at least things that we don't really talk about too much. The cecum is actually a smaller projection. We're moving from the ileum, again, the last portion of the small intestine. You've got the cecum, which is not as developed in humans, but much more developed in herbivores. Look at cows, for instance, have a very well-developed cecum. If you look at your earlier slides, you saw species that have very well developed, and I'll talk about a little bit about that when we get to that section. We'll see the ascending colon, the transverse colon, and then the descending colon. So this is wrapping all around the cavity for the small intestine. The sigmoid colon will wrap around, and the last piece we'll talk about is rectum, as well as the anal canal. Looking at the large intestine, we don't have any of the plicae circularis or the villi that you saw in the small intestine. So even though we're going to continue with some of the absorption, the thing that we typically see really is just the microvilli. So here you see the same layers, the muscularis, you'll see the longitudinal, you'll see the circular muscles within the muscularis, you'll see the submucosa again, and then the epithelial cells, the columnar epithelial cells, are going to be present in the mucosa. But right up on top, you'll see the microvilli. Again, for the purposes of absorbing. And what we're absorbing in the large intestine is mostly water. Other cells that are also present, you can see some of our goblet cells. Goblet cells that are embedded within the mucosal layer produce mucus. And that's to create, again, that thick mucus layer that's present right up at the very top. I'm not going to really talk too much about the the smooth muscle within, but basically what's namely present within large intestine are what are called Teniae coli. And the Teniae coli are basically these long ribbons of smooth muscle. And what they do, and let me show you on an earlier slide, here you can see the Teniae coli that is this, again, this long ribbon of muscle. And what that does, it basically helps scrunch up. They contract to create these little different segments that you can see. So in the cases where the muscle is relaxed, you get more of a longer length of the small intestine. And when these contract, they help kind of scrunch it all up together. And why that really is the case? Why do we have that? Well, it creates what are called these small pouches called haustra. And that haustra allows the contractions to take place within each of the segments. So as the contraction takes place, it helps move the contents of the small intestine to move up through the ascending colon, through the transverse, and down the descending colon. So these are what are called haustral contractions, and they help stimulate movement of leftover stuff through the large intestine. And these haustral contractions are things that take place. Again, we'll talk about what stimulates these, but they typically take place right after eating. So if you ever eat something and you notice all of a sudden you're getting all these sort of bowel movements, what is that happening? That's mostly not only the stomach movement, the mixing waves that are taking place in the stomach, but also the large intestine. So it's all ramping up. Once you eat something, that's going to feed sensory information to the central nervous system and start ramping things down the alimentary canal. And this is an exact case of that. The cecum is just a small pouch. I'm not going to talk too much about that. The colon, which are all parts of the large intestine. Again, the main purpose of these, especially the cecum, is to contain what are called beneficial bacteria. So again, this is still consistent with the external environment. We do have tons of beneficial bacteria in the large intestine that help the breakdown of stuff that we don't normally break down. Another good example of that is E. coli. We have plenty of E. coli present in the large intestine. It's something that we don't produce E. coli. E. coli is just present in there to help break down those additional nutrients. They help break them down and release the vitamins that allow us to absorb those in place. It's the sort of the spin for where probiotics come in, things that are present in yogurt. I know there's a lot of even journal articles that support fermented foods like sauerkraut, kimchi, and other fermented foods that are good for you because they house this beneficial bacteria and they help sort of replenish. If you ever hear some of those buzzwords that things like kombucha. Kombucha has tons of, even apple cider vinegar, for instance, tout that they're full of probiotics that come in and replenish the gut flora. That's exactly what they're talking about, is the presence of that bacteria in there. Now, does it really provide any benefit? I can't necessarily answer that because I know that's what we're trying to figure out. But I think the general consensus is, if you already have normal gut, if your diet is pretty normal, you already have the bacteria there. There's no sense in trying to replenish the gut bacteria because you're not flushing them out. You're not lacking bacteria. You're constantly always producing it. Typically, in cases that I have read about that where they may be important, when you take antibiotics. Antibiotics kill not only only bad bacteria, they also kill a good amount of good bacteria. So antibiotics can definitely disrupt the gut flora, and that's where some probiotics can come in and help replenish that. Again, does it really help? I don't really know, but all of these things are really more homeopathic remedies that may not necessarily, they may or may not have any actual medical benefit of any kind, hence why they're considered supplements. With that, there's certain diseases like cholera that result in extreme diarrhea. And a lot of that is flushing too. If you ever see in cases of diarrhea, you can see heavy mucus. If the mucus that's heavily present in diarrhea can contain a lot of that E. coli bacteria that's flushed out. So in responses where any disruptions of the GI tract come in, our response is pretty much to flush out whatever we're trying to get through our system. So you'll see typically things that are not digested, you get a lot of fluid that's expelled out and a lot of mucus that comes out to essentially restore and help start the process of absorption all over again. The rectum is the last portion that we'll look at for the last 5-10 slides. The rectum is the last portion of the large intestine. So now we're making our way. We know we've done a good amount of absorption of water. We're now end up with compacted remainders of what we did not absorb. So what typically would you see is present in what's now known as feces? A lot of the stuff that we couldn't absorb. We have cellulose that's present within plant material. If you ever read on the back of food items, you'll see fiber, a lot of dietary fiber or non-soluble fibers. That's stuff that we don't necessarily absorb, but they help contribute to good diets, as well as the sort of bulk of what's present in your feces. So they help with the movement of bowels. The other thing we'll take a look at the other components. Looking at the rectum, again, the rectum is the last 8 inches. Here you can see the real last portion of the last 1 inch is called the anal canal, and that's this portion right here. And this anal canal actually have these ridges, and these ridges are these longitudinal folds that contain a bunch of arteries and veins in that area. So this area is very rich in blood supply, hence why suppositories are used. We typically, suppositories are medications that are covered in, I actually don't know what they use as a binding material, but it's typically kind of fatty. I think it's almost like coconut oil or whatever they use. Something soft, but when inserted into the anal canal, it's typically used to melt into, and then doesn't really interfere with the anal canal, but the medication can get absorbed due to that rich blood supply. I just recently watched a terrible show called, it's not really terrible, Shameless. Has anybody ever seen Shameless?
Yeah.
I think I got as far as like the end of season 7, beginning of season 8. Not to really spoil anything, but I think the father's like this really bad alcoholic, and he gets to the point where he can't really drink alcohol anymore because of all the irritation and all the whatever's happening in his esophagus, and he ends up puking quite a bit of blood. So he's just like, well, you got to get it in some way, and he tells his son to absorb alcohol the other way, and the other way was to use a funnel and a tube and to funnel alcohol through this way, and that's our way of absorption. There's a lot of drugs that utilize suppositories that help absorb this drug slowly, but that technically is the other way of doing it. It's maybe not a preferred way, but if you need to get medications in, this is your way of doing it. And certainly to kind of tie in with the guy in Shameless, this is his way of being able to get alcohol into his system. So with that, moving at the last portion, let me go into, talk about that? I will talk about the defecation reflex. Oh no, okay. The one thing on here that I want to talk about is the internal anal sphincter as well as the external anal sphincter. So there are two sphincters that are present in the muscularis layer. So the internal anal sphincter is a little bit deeper. The external anal sphincter is the muscle that surrounds it. So this is called the internal, this is considered the external. So what you can see on the image to the right, the internal anal sphincter is what's going to be able to detect. There are stretch receptors that help give feedback if the anal canal is starting to fill up with feces. Okay, so that's going to feed back and let us know. Okay, anal canal is starting to fill up, but we still have voluntary control over defecation, and that is the external anal sphincter. This is all voluntary muscle that comes in. This is our way of basically pinching off and saying, don't release, bless you, don't release any of the feces just yet. So we can override in cases with especially babies don't actually have very strong motor control. Hence why they have no control over defecation. So in those cases, the internal and external sphincter work hand in hand, or actually the external doesn't really work as well, but in babies this causes release of feces whenever they, I guess not really feel like it, whenever babies just defecate. They defecate not at will, they just do it whenever they want to. The external anal sphincter is something that is voluntary, something that is learned that we do in order to prevent defecation. And once the stretching comes up to the point that we fill up with quite a bit of pressure in the feces, this is where the internal anal sphincter starts to pick up and sends information back, letting us know that we really need to defecate. Okay? But the external anal sphincter is what we use in order to override that. So it's a mixture of both voluntary and involuntary feedback. Now, the large intestine, just to kind of finalize the functions of the large intestine, is to think about what we're doing with all the fluids. Where does the bulk of the fluids absorbed? We mentioned 7 liters, 1.5 from saliva, 3 from gastric, we have 1.5 in pancreatic, and I'm missing 1 bile, that's right. 1 liter from bile. That comes out to 7 liters. And on top of that, the additional 2 liters that you drink, 2 liters, that comes out to about half a gallon, about 64 ounces, divided by a cup. Cup has 8 ounces. That's 8 cups of water per day. So if you have heard of why do you need to drink 8 cups of water, well, that's technically how much you should be drinking per day. So about 64 ounces. So on top of that, that's about 9 liters that enter the alimentary canal. We have to absorb the remainder of that. And again, that's part of the sort of evolutionary process for us to be able to absorb our fluids. Because if we were losing that much fluid, we'd dehydrate in a matter of like a couple days. What we need to do is to look at where that absorption takes place. Now the absorption of where that takes place is really the small intestine. The small intestine absorbs 8 out of those 9 liters. The large intestine does the final 1 liter of absorption. So that the final bit of what we have left is about 100 mils of water left over in the feces. Okay. This is our way of being able to conserve. If you look at any of the other species, especially in desert species, I know like desert rats have the ability to basically eliminate, and this is not even really covering the last portion of excretion because we still need to talk about urination. But this is our way of being able to conserve fluids. So some of the desert rats actually can bypass defecation. They can actually eliminate very hard pebbles, which will really eliminate, or at least reabsorb most of the water that takes place. And they can end up peeing out like uric crystals, so basically to really conserve on water. And that's basically what we're doing. We want to utilize that water so that we can continue reusing that to maintain normal blood pressure and maintain normal tonicity of our blood. So don't confuse that. Most people like to think that the large intestine does the bulk of water absorption. it's really the small intestine. Looking at the composition of feces, most of that, like I mentioned, is stuff that we don't absorb. But there's still a good amount of calories that are present. Calories are basically the units of energy in a certain amount of food or whatever material you're looking at. There's still a lot of usable energy. What we've been able to do through the process of breaking down those nutrients is we're releasing the energy contained within the chemical bonds, okay, and the state of energy of those molecules. We're able to utilize that to produce ATP. We can get glucose. We can get glucose from it, and that will help fuel cellular respiration. Looking at the breakdown of that food, what's left over in the feces can still be used as a viable food source. So even though feces are what's eliminated, you'll see that there's other species that can come in and still utilize the energy that's still contained within, which is all part of the sort of life cycle. But nonetheless, the rest of the other components of feces, most of that coloration, that brown coloration, comes from bile. That's leftover bile as well as bilirubin from the breakdown of our red blood cells. The odors that are present in feces, typically present from the bacteria. This is leftover bacteria. This is the gut flora that's present to help the breakdown of our food. Some of these cells, this particular slide goes into the other beneficial bacteria. We have tons of different microorganisms, and the bulk of our feces really is those leftover cells or leftover microorganisms. So there is a lot of stuff that talks about. I know there's certain Aboriginal cultures that look into ingestion of feces. I don't know where I read this. It was like somewhere in the back of my head, but obviously the dangers behind that are the E. coli, things that are typically not something that we do want to ingest. But like I said, the presence of those bacteria help the breakdown of leftover food. You can see vitamin K is something that's also important, biotin, other amino acids that are all absorbed due to that beneficial bacteria that help break this stuff down. The last couple things I want to talk about are the reflexes that are involved. The reflexes that are involved that help govern the motions of the large intestine. So now that we know how the large intestine helps create these haustral contractions, let's talk about what triggers it. So the things that we talked about earlier also play a major role. You'll see the two autonomic reflexes are the gastroileal reflexes as well as the gastrocolic reflexes. The biggest bulk of what's going to create these haustral contractions is gastric filling. Again, looking at the chemoreceptors located in the stomach, looking at the stretch receptors in the stomach. Once food enters the stomach, that starts the process of all these peristaltic movements, whether they're mixing waves, whether they are whether the release of hormones, our cholecystokinin, our gastrin, the release of pancreatic juices, release of bile, causing our segmentations in the small intestine as well as the haustral contractions taking place in the large intestine. All of these reflexes come into play to help move and propel that stuff down the alimentary canal. The big ones, though, are the gastroileal reflex and gastrocolic reflexes, and our next slide talks about those. The gastroileal reflexes is just peristalsis in the ileum that causes relaxation of the ileocecal valve. Not something I'll really ask you, but basically what all it does is it pushes stuff from the small intestine, the last portion, the ileum, pushes it right into the cecum. So this is our first bit, when we move from small intestine to large intestine, that causes large haustral contractions in the large intestine. The other one is a gastrocolic reflex, again, promoting a lot of muscle movement within the transverse colon. So you get these pretty much where is it taking place? Pretty much within the transverse colon. So as gastroileal reflex takes place right here, when the stuff is present within the transverse colon, you'll get a lot of contractions that are taking place, and that is just right up above. If you ever eat something and you feel the sort of bowel movements, listen to anybody. If you ever okay, never mind, I won't mention that. But really all I was trying to get into is like if you ever hear somebody eat, or if you know somebody eats, listen to their stomach, and then I realized, oh, that's really creepy. Don't do that. But a lot of the motions you can hear that are taking place, people like to think it's the stomach. It's actually not the stomach. This is the transverse colon, again, the gastrocolic reflex that's taking place due to the presence of food in the stomach. That is our way of ramping up to get the small intestine to start moving. And again, they work all through the 10 E. coli that help promote those haustral contractions. These actually take place quite a bit, and when do those reflexes take place? Right after a meal. So they just again, due to the presence of a meal, once food enters the stomach, starts triggering these contractions. And those contractions that are taking place can start increasing the pressure within the large intestine, start increasing the amount of pressure in the anal canal, which again triggers feedback into the involuntary sphincter, giving us the feeling of the need to defecate. So if you know of anybody, and I certainly know a couple people that once they start eating, immediately they feel they need to go to the bathroom. Why is that? Haustral contractions encourages that. The defecation reflex is basically everything that I've talked about that results in the process of defecation, again, the elimination of a feces. Food in the stomach stimulates peristalsis, we already described. Moving food through the intestine into the rectum. The pressoreceptors, again, these are pressure receptors. They're like baroreceptors, but they actually just detect pressure. So as the feces presses up against these rectal pressoreceptors, that causes distension as well as the longitudinal muscles. And I'll show you back in our prior slide of how that takes place. So there's longitudinal muscles again that I mentioned that are on the outside of the muscularis. What happens as the pressoreceptors come in and start filling up with feces, this starts pressing against these pressoreceptors that ends up shortening the length of the rectum. So the longitudinal muscle starts to scrunch up altogether. And that actually causes positive feedback because that presses up against the internal anal sphincter. So as this starts to fill up, contraction of the longitudinal muscle, increased pressure, positive feedback. Increased pressure then sends feedback information letting you know that you do have that urge to defecate. And again, all that defecation is all managed through contraction of the external anal sphincter. And then, of course, with the release of that external anal sphincter is where defecation actually takes place. And that's how we end up eliminating all of our wastes. With that, I've got nothing left. That last slide is something I've been meaning to get rid of, and I don't know why that's on there, but colonoscopy, I was just looking at what they would do. I think what I really wanted to do was just illustrate what the look of would look like in the large intestine. You can see the different segments that are present within, and again, that's all due to the 10 E. coli that help contract. So just know for a colonoscopy, they do tell you not to eat anything, otherwise it looks like that to the right. All of this helps summarize. This entire table goes in and summarizes all of the different organs. So use this. You have homework assignment that helps go through each of those segments and we'll talk about the different enzymes. Use this to your advantage, and good luck on studying. Have a good Thanksgiving. Think about all these things as you're having your Thanksgiving dinner, and I will see you guys on Tuesday, where we'll